Hi, this video will show you how to run Tomo in Flatirons. Now the Tomo in Flatirons is both for 2D and 3D. There's really no difference between them, how you run them. What we're going to do is we're going to start off with a set of pics. So this is our demo data set, and as you can see from the screen, I have a shot record up and it has a full suite of pics. And if I bounce around the survey, you'll see I have a few missed pics up here, for example. I'm not going to worry about those. The purpose of this is to show you how to run it. I'm not going to try to come up with the perfect Tomo on this particular data set, but I'll probably do a pretty good job anyway. So anyway, so I have a full suite of pics, and there's some questions out there about should all the offsets be picked? Do I need the inner offsets? Do I need the outer offsets? My personal philosophy is the more data you have to the inner offsets, the better off you are, because that's where your slow velocities are. You know, your inner offsets are associated with your shallow layers. And the shallow layers are the slower velocities, and the slower velocities cause more of your statics problems. So the better the pics and your shallow offsets, the better off you are. So in this data set, you can see I'm looking at all my traces for this shot and for other shots, and you can see I have pics all the way into zero offset. This would be my nearest offset right there. So before we get into the Tomo, the first thing you're going to need, though, the program's going to ask you for the starting velocity near the surface and then an ending velocity at the bottom of your model. And the best place to get these is from the branch assignment window, or at least for me it is. So let me go into the branch assignment window and I'll show you how to do this, how I do it. We're going to go in here and we're going to use the pics since they're fastest. And I'll just click here. And as you can see, I have a lot of missed pics, but I'm not going to, the algorithm isn't bothered by those. Another common wisdom out there is you have to have perfect pics. Well, our Tomo algorithm in Flatirons is no more sensitive to missed pics than any of the other algorithms. And the kind of missed pics you're seeing on this screen here, where my good pics are down here or my bad pics are up here, are definitely not of the order that are going to cause any problems for our algorithm. So anyway, so the point is, what I'm going to try to do here is I want to establish what my starting velocity is and my ending velocity. And these are just ballpark numbers. So I'm going to lock in here. And I'm going to flatten out this refracted arrival. In this case, as you can see here, it's about 5,500. And my final velocity here is about 6,800. So we're just looking for ballpark numbers. So I'm going to say 5,000 to 7,000, just to encompass those. But if I said 5,500 to what was the velocity again? 6,600 or so. Or if I said 5,000 to 6,000, the program would still be able to handle it. It's just it would just take a little bit longer perhaps to converge. So anyway, the only reason I'm doing this though is to have a look at what my inner velocities are, which are from zero out, and that's about 5,500 or so. And then my final velocities I'm seeing in my model, 6,500. And I know this data set pretty well. As you can see, it's really not varying all that much. So I'm going to say 5,000 to 7,000 and be somewhat generous on there. So I'm going to cancel that, and now I'm going to go back to I'm going to bring up Tomo, 3D Eikonal Tomography. I'm going to create a new model, and I'll just call this Chuck 1, because I'm Chuck Diggins, and I just name it after myself. And this happens to be in the feet system. What is it's metric and I don't know, feet. So I'm gonna do a 200 foot by 100 foot, 200 foot X and Y, and 100 foot vertical. The nice thing about this particular algorithm compared to some of our other algorithms we've had in the past in our other software is that you can have a different vertical spacing than you can in horizontal. So your X and Y spacing in this case is 200, but I could do, say, a vertical node spacing with 10 if I wished. So for the purposes of this, though, I'm going to speed it up a little bit. So we'll do 200 and 100. And I'm going to say, let's go down to 600. Now, I don't have any real good guidelines for this. Lots of times you'll run the program and you'll see how deep the program went, and then you'll decide whether it was too deep, or can you cut back on the depth, or did you need to make it deeper. Right now I don't have any real guidelines for that. But I'm going to have 100 vertical spacing and a node depth of 600 means I'm going to have 6 depth steps, which is not all that much. So this is not going to be a high resolution model. So I'm going to start off with 5,000, I said, and I'm going to go to 7,000. So I'm going to start a model. This is not a marine survey, of course, so we don't have to worry about this stuff. We'll say create a new model. Now, these happen to be some elevation errors that I never corrected in the program. There's like 8 or 10 shots that have errors in their elevations, and that's what these are, so we don't have to worry about those. They're not important for this. And so the first thing we're going to do after we create a model is we're going to, well, here's a profile of the model just as it looks. There's no tomography been run yet. This is the initial model. And you can see here's our surface topography, which is pretty mild elevation change. And then this is our model. This is the velocity gradient that we are hanging off the surface down to a few hundred feet. And now we're going to update. And update is where we actually run the model. My offsets range from 0 to 6,000. My very inner offsets are probably not valid, so I'm not even going to use those. So it happens that these are the defaults and they're fine. And 10 iterations is fine. Node radius spacing is fine. Depending on how many threads you have on your computer, this computer happens to have 8 available to it. So I'm just going to say 6. And we're not going to worry about any of these other things down here. Those are advanced options. You can play around with them if you want. So I'm going to run this and see how fast it runs. It should only take a few minutes on this particular data set, so I'm not going to bother to pause it. This is a very efficient algorithm, by the way. It does run. It's an Eikonal tomography. And we find in practice that even on really large data sets, like a billion traces, we can pretty much run this at least overnight, a few hours. So it's pretty efficient for that purpose. I'm running on an iMac right now, a standard iMac computer. So this is the model that we were looking at before, but now I have a new model. So I'm going to this is now down here. This is our ray density. This is where where the rays spent most of their time. So as you can see here, we really didn't have anything happening beneath 500. All the rays came down, returning through the model and spending their time mostly at this level and at this level, but nothing really underneath 500 elevation or 600 feet deep. So at this point, we're going to compute some statics. So I'm going to say the base of my weathering is really right about here. I'm going to say about 300. So I'm not really worried about where the ray density is. I'm really worried about where the base of the slow velocities are. And the slow velocities in this case is about 300. As you can see beneath there, everything's about 6,000, but above there it's ranging from 3,500 and even over here to 3,000. So I'm going to say, let's say at 300. So I'm going to say my base of statics is fixed elevation of minus 300. And if we set a fixed velocity, what that means is a velocity that's constant. So like you can see here, like 5,200 would be this yellow line. And there's really no saying where. Over here it's pretty obvious where it would be, but over here it's probably in here someplace. Wherever the velocity changes over 5,200, that would be the base of the intermediate datum. So I don't use that a lot, but I have used it a few times. Or you can do fixed depth, which is relative to the surface. So right now these are the 3 options. And keep that, apply residual correction, okay. Force statics to be 0 mean. I like to do that just so I can compare it to my other statics or no statics at all. You can rename your statics here. I'm going to just call it that. I'm going to do a replacement velocity, however, that is comparable, close to the velocity in this orange zone here, which is about 6,000. So let's say 6,000. And let's put a datum of about 100. But because I'm going to do 0 mean, the datum elevation itself is going to be compromised a bit until I turn this off. But right now, so I'm going to do Tomo 3D, intermediate datum down to here. So I'm going to compute velocities from here down to here using these velocities in the model. And then I'm going to go back up to the surface, up to 100, which is right near the surface here, at 6,000. And those will be my statics. Compute statics, very fast, and that's it. Now, one of the things we can do in the program really quickly is we can actually apply the Tomo model, Tomo to our solution. Tomo solution to our traces. So I'm going to, over here under defaults, you can see apply options for a 3D Tomo analysis. And a perfect solution here would be flat on 0. And as you can see, so what I've done is I've applied the Tomo model, and it's not doing a bad job. And this is for all offsets. You can see this from 0 all the way out to 6,000. There's a few places, like for example, I have some problems with, there's a geometry problem. I'm not going to worry about that. That's a subject of another lecture or video. But for the most part, this program has done a really good job. And the places where it has the most problems are the very, very inner offsets. So let me change this offset range to be like a 400 to 6,000. Try 800 to 6,000. Okay, you can see it's a little better here. Let's see here. Okay, well, anyway, so that's how you run the Tomo. It's pretty simple, exact, identical in 2D as in 3D. There's really no difference, same algorithm. So thank you very much.